I welcome you all once again to this lecture on relative velocity. We will take off from where we have stopped yesterday. So this concept which I am going to take up today, it's a bit involved in relative velocity, but we are going to see that it's a very important concept. Many problems are based on this particular concept. I would like to start this concept with one problem. I have put the problem here. A cat always approaches a rat with a velocity of 5 meters per second. The rat can move with any speed in any direction. So cat is always approaching the rat with a velocity of 5 meters per second. Rat can move in any direction with any speed. See the statement here, it can move with any speed in any direction. If the initial separation between them is 5 meters, that means the initial separation between the cat and the rat is 5 meters, then we have 4 options here. The cat will never catch the rat, that is option A. The cat may catch the rat, see the word may, and the cat will definitely catch the rat after 1 second, and the cat may catch the rat but not in 1 second. Generally, if we think about this problem, we might come to the conclusion that the cat may catch the rat. See, after all, the rat can move with any speed. It can move with any speed, which means even 10,000 kilometers per hour is possible. In any direction, the rat can move in any direction. So we might think that cat may catch the rat but not in 1 second. This may be the correct answer, but actually this is not the correct answer. The correct answer is the cat will definitely catch the rat after 1 second. How? How on earth did I come to this conclusion that the cat will definitely catch the rat after 1 second? See, after all, the rat can move with any speed in any direction. But there is a word in this problem on which you must focus your attention. Always approaches. This word approach has got a special meaning when you come to relative velocity. When you take up this topic of relative velocity, the word approach has got a special meaning. So let's see what it means. First, if there is a cat and if there is a rat, you must join them by a straight line. That is the first thing. And then you must take the velocities along this line. So there is this cat, there is the rat. You take velocity of rat along that line. Suppose the rat is moving with 10 meters per second. Well, its velocity along the line is 10 cos theta. Component of velocity along that. Similarly, if the cat is moving with 20 and if this angle is phi, the cat's velocity along that line is 20 cos phi. Along this line, see how fast they are closing in. So cat's velocity is 20 cos phi, rat's velocity is 10 cos theta. The approach between them, when do we say they approach? When cat is moving faster along this line compared to rat. So in that case, the cat is coming closer to the rat. That is called approach speed. Okay, so cat's velocity along the line joining them must be more than rat's velocity along the line joining them. Then you say the cat is approaching the rat. On the other hand, if rat's velocity along the line joining is more than cat's velocity along that line, we say they are separating. So when I say the cat always approaches a rat, that means cat is always coming closer towards the rat with a speed of 5 meters per second. It is always coming closer towards the rat with a speed of 5 meters per second. Let me explain this. Suppose if rat is going with 2 meters per second in some direction, cat is going with 7 meters per second in the same direction. Why? Because cat is approaching the rat with 5 meters per second. Suppose if the rat increases its speed to 20,000, then cat's speed should be 20,005, because the approach between them is always 5 meters per second. So you see, the word approach has got a special meaning. The rat may move in any direction with any speed. Cat's speed will always be more than rat's speed with 5 meters per second along the line joining them. That is the meaning. So now you see, I, for the sake of visualization, take a rod of length 5 meters. On one end is the rat, on one end is the cat. The cat is going on the rod with 5 meters per second. The cat is moving on the rod with 5 meters per second. So if you are standing on the rod, the situation is very simple. Cat simply goes away and catches the rat. Because cat is traveling 5 meters with 5 meters per second, the time taken will be distance by speed, 5 by 5, 1 second. The cat catches the rat in 1 second. Now suppose I kick this rod. So this rod is moving in a very complicated way. It is moving in certain complicated way. That means if you are seeing from the ground frame, if you are standing on the ground and seeing this, you see the rat also moving along with the rod. You see the cat also moving in a very complicated path. So for example, you see it like this. If you follow my fingers, you will see it going like that. You see, the cat is coming closer to the rat. So from the ground frame, you might think that they are going in a very complicated path. But actually what is happening? You stand on the rod and see. The cat is simply going towards the rat. Okay, from the ground frame, the rod is also moving in a very complicated way, so it might look very complicated to you, the motion of the rat and the cat. But if you see it from the rod frame of the rod, the cat simply has to move on the rod. So now you see, if I give some speed to the rod, that is as good as giving speed to the rat, and some speed to the cat also. But the cat is always approaching the rat with 5 meters per second. So the time taken by the cat to catch the rat will be 5 by 5, which is 1 second. So this is a very tricky concept. So in all my further problems, I will take the example of this rod because it is very convenient to visualize if we take the example of this rod. Now, there is a problem in most of the books which we are going to solve now. It's a very tricky problem. I would solve in 3 ways. But the understanding that is required to solve this problem is this approach, concept of approach in relative velocity. So the problem says there are 3 particles at the corners of an equilateral triangle. 3 particles, this is particle 1, particle 2 and particle 3. All the 3 particles are at the corners of an equilateral triangle. The side of this equilateral triangle is A, and each particle is aiming and going towards the other particle. So 1 is going towards 2, 2 is going towards 3, 3 is going towards 1. And all these particles are going with velocity v towards the next particle. So if you try to formulate the path in which they are going, if you try to draw the path in which they are moving, after a small time, one would have come to this position because it is moving towards 2. 2 would have come to that position because it is moving towards 3. And 3 would have come to this position because it is moving towards 1. So if I join them now, the situation looks like that. The situation looks like that. So after a small time, the positions of these particles have changed. After a further small time, again 1 should go towards 2. So it should go in this direction now. 2 must go towards 3 in that direction, and 3 must go towards 1 in this direction, And you can see that if I join them now by a line, by a triangle, it looks like that. After some more time, this again moves towards that. So you see, if you join all these, you will get the path in which these particles are trying to move. That is the path in which they are trying to move. Ultimately, by symmetry, they would meet at the center. I can call that either centroid or circumcenter or orthocenter or incenter, because this is an equilateral triangle, all these four coincide. So they meet there. Now we have to find the time taken for the particles to meet. This is the question. We have to find the time taken by the particles to meet. Now how do we find this? Because the path of these particles seems to be very complicated. So I cannot use my normal displacement by time and so on, because we don't know even, for example, distance traveled by speed. If I want to use that, I should calculate this path length. That's very difficult. But here, if you look carefully, all these particles are going with a velocity v towards the next particle. So let's see that. 1 is going towards 2 with a velocity v. 2 is going towards 3 with a velocity v. Let us join 1 and 2 by a line. This is the line. I am joining 1 and 2 by a line. Let's see what is velocity of 2 along this line. The component of velocity of 2 along this direction. This angle is 60 because it's an equilateral triangle. So the component of v along this direction is v cos 60, which is v by 2. And the component of v perpendicular to that line is v sin 60. So I can say it is v root 3 by 2. Now, this situation, what I have shown, 1 and 2 are approaching. You see here, I am using the word approaching because I am talking about their speeds along the line joining them. Whenever you talk of approach or separation, you must join the particles by a line. So we are talking about the approach or separation along the line joining both the particles. So they are approaching with a speed of v plus v by 2, because this is coming with v, that is coming with v by 2. So after 1 second, the distance gets shortened by v plus v by 2. So their approach speed is given by v plus v by 2. So it is given by 3v by 2. Now this statement is true at every moment. Even in the initial moment, they are coming with 3v by 2. After some time also, they are coming with 3v by 2. Can you see that? This is going with speed v, that is going with speed v in that direction. So this component will again be v cos 60, which is v by 2. So they are again approaching with v plus v by 2. Again after some more time, they will be approaching with v plus v by 2. So they are coming closer, approaching with 3v by 2. And initial separation is a. Finally this separation is destroyed. So they are killing this separation with this approach speed. So the time taken will simply be this distance, initial separation between them, by approach speed, which should be 2a by 3v. Now I have written it like this, but let us see this conceptually, how this works. Suppose you join 1 and 2 with a rod. Okay. Now 1 is moving on the rod with a speed v, 2 is moving on the rod with a speed v by 2, and rod itself is rotating with v root 3 by 2. Isn't this situation similar to the original situation? See, after all, 1 has a speed v. So I am saying 1 moves on the rod with speed v. 2 has two components of velocity, v by 2 and v root 3 by 2. So what I am doing, v by 2 is the speed along the rod, and I am making the rod itself rotate with v root 3 by 2. So the net speed of 2, when I see from ground, is v by 2 this way on the rod, and speed of rod itself is v root 3 by 2 that way. So the net speed of 2 is sum of these two. Now keep rotating the rod and reduce the length of the rod. So it is initially like this. So you do that. Keep reducing the length of the rod. So ultimately what is happening? The particles are moving along the rod You need not worry how the rod is moving. The particles are moving along the rod. The separation, the rod length is A. They are approaching with V plus V by 2, 3V by 2. So time taken after all, because they are moving on the rod, time taken by them will be this separation by the approach speed, which is A by 3V by 2 or 2A by 3V. So you see, with the help of this rod connecting particles 1 and 2, I am able to explain this concept beautifully, which is in fact very difficult to understand if we do not take this rod approach. This is one solution. In fact, if you go through books like H.C. Verma, he gives this solution, and there is also another solution given by H.C. Verma. So let's try to understand that solution. Join one of the particles to the centroid. So the angle between this line and velocity of the particle is 30 degrees, because this line is angular bisector of this equilateral triangle, which we got by joining the particles. So the velocity of this particle towards O, I call O as the central point where they meet. So velocity of this particle towards O is V cos 30. So I can say that velocity is V cos 30 or V root 3 by 2. This is not only true now, it is true at every moment. For example, when the particle is here, again you join in the particle to the point O. Again it is approaching O with V root 3 by 2. I call this approach. Why? Because point O is at rest and this particle is approaching point O. Remember, approach is along the line joining them. So this particle is approaching point O with a speed of V cos 30 again, which is V root 3 by 2. And even at some other intermediate position, it's always true. The particle always approaches point O with V root 3 by 2. Now again I can use the concept of a rod. One end of the rod is fixed at O, other end is here, and the particle is moving on the rod. The rod may have some other velocity, that's different. But the particle is moving on the rod itself is moving. So if you see the total velocity of the particle, it is velocity with respect to rod plus that of rod. Okay? But we are on the rod frame now. I am standing on the rod. So when I am standing on the rod, what do I see? I just see the particle going that way. So we must get this length. So how do I get that? This is nothing but A by 2. And this is the hypotenuse of this right triangle. Can you see that? So I am showing it. This is a right triangle because this is 90 degrees. So this is the hypotenuse of the right triangle. If this is A by 2, this is A by 2 by cos 30. So I can say AO is A by 2 by cos 30 root 3 by 2, or I can say A by root 3 in general. So that is the length of the rod which I am connecting. On that rod, this particle is moving like that. The rod is also rotating, moving in some fashion, because with respect to ground the particle is going like that. So the time taken will simply be AO, which is A by root 3 by speed, which is V root 3 by 2. So you can see that is 2A by 3V again, which is what H.C. Verma gives, but to understand it from there is very difficult. He is trying to tell you something, but then without this rod formulation, without this example of this rod, it's very difficult to understand that. So this is the problem.